Alright, in our last video, we looked at parallel RL circuit calculations. In this video, we are going to look at changes in frequency and how the circuit is affected. So, for this one, we are going to change our incoming frequency from 18 kHz to 40 kHz, which is an increase. Now, with that increase in frequency, we know that our two inductors, L1 and L2, their ohmic values are affected by changes in frequency because that formula is frequency times inductance times 2 pi. So any change in either inductance or frequency is going to change the inductive reactance. Now in this case, we are varying frequency, and it is indeed going up. Now that formula, if you remember, is a straight multiplication formula, which means that anytime you put a bigger number in, you get a bigger number out. Anytime you put a smaller number in, you get a smaller number out. All right, and so we had our original inductive reactance for L1 of 4.52 k ohms, and of course now it has gone up because frequency has gone up to 10.05 k ohms. Now our second inductor had an ohmic value of 3.17 k. And of course, again, we are expecting that to go up, and it did, to 7.03 k ohms. Now with both of the ohmic values going up, we're expecting the total to go up as well. It will still be smaller than the smallest value because, again, it's an inversion formula, but it is going to be larger than it originally was. So it originally was 1.86 k ohms, and now we see that it is indeed larger of 4.14 k ohms. Now again, we're going to put this into our impedance formula to get a total ohmic value for the circuit, which of course we're expecting to go up because now that smallest value is much greater than it was. It was 1.86 k ohms, and now it's 4.14 k ohms. So that's considerably larger than it was. So we're expecting to see something less than 4.14 k ohms because it is still less than 9 k ohms, which is the ohmic value of our resistor. But it's much greater than the original number was. And let's take a look at that. And we do have now 3.77 k ohms, which is greater than it was originally. Now, since our ohmic values and our currents are inversely proportional, we are expecting the current for this circuit to have gone down because the ohmic value went up. And if you look at the math on that, you will see that current did indeed go down, and it is now 3.18 milliamps. For simplicity's sake, I left the formulas off of this one. If that's messing you up in any way, feel free to work some of these numbers out on your own using the same process that we used for the previous video. So in other words, to get total current, you would just take 12, which is the applied voltage, divided by that new ohmic value of 3.77 k ohms, which is what gives you the 3.18 milliamps. Okay, so frequency doesn't affect the ohmic value of our resistor, and because it doesn't affect the ohmic value of our resistor or voltage, and current is voltage divided by resistance, if neither of those values change, we would expect current also to stay the same. And it does indeed. So we have a current that remains the same at 1.33 milliamps for branch 1, which is where our resistor is. Now, on our two branches that have inductors, we're expecting those currents to change. And the reason is both of those ohmic values change. Both L1 and L2 now have greater ohmic values. And so if they have greater ohmic values, we are expecting them to have smaller currents. So when we look at those, we see that the new current for branch 2, actually, I apologize for that typo there, is 1.19 milliamps, and the new current for branch 3 is 1.71 milliamps. And again, I apologize for the typo. So they both have gone down, just like we suspected that they would. Now, of course, if we were going to do the current route, we would figure out our individual ohmic values and our individual currents, use the same process we used in the previous video, and we would take our original resistive current, because it hasn't changed, and our new currents through branch 2 and branch 3, the combined value, which is now 2.9 milli, and throw that into our formula, and we should get exactly the same thing of 3.18 milliamps. Again, I don't know, I think we talked about this in our series, ohmic value calculations, but you'll know that you're right, or at least have a good opportunity to be right, if you look at your formula right here, this formula, and you find that your total is bigger than the biggest value, but not as big as the two of them added together, right? If I added the two together, I would get 4.23 milli. And you'll notice so that 3.18 milli is larger than 2.9 milli, but not as big as the two of them just straight added together. And that's kind of like a way to double check and say, oh yeah, I got it right. All right, and we'll notice too that all of those voltages stayed exactly the same, right? Because in parallel circuits, unless you change that incoming voltage when you have a branch that only has one component on it, you're going to drop all that voltage on that branch. So you would have 12 on every one of them. And so that didn't change at all. All right, next we're going to look at frequency going down.